Hello. In this video, we will see how resting membrane potential develops. This video is divided into two levels. Level 1 is for beginners, where we will see the very basic concepts behind the origin of resting membrane potential. And in level 2, we will see the same concepts in more detail. Let's get started. Under the resting condition, the inside of the cell is electronegative. For example, the resting membrane potential of a neuron is minus 90 mV. The main factors contributing to the resting membrane potential are diffusion of potassium through potassium leak channels and electrogenic nature of sodium-potassium ATPase pump. First, let's see the diffusion of potassium. The cells contain potassium leak channels. These channels are open even during resting state. Now, we know that potassium concentration is higher inside the cell than outside. Due to this concentration gradient, potassium diffuses out of the cell through these channels. Now, potassium is a positively charged ion, so its exit from the cell makes the outside of the cell electropositive and inside of the cell electronegative. This is the main contributor to resting membrane potential. Apart from this, sodium-potassium ATPase pump also provides some contribution. During each cycle, it moves 3 sodium ions from inside to outside and 2 potassium ions from outside to inside. Thus, in each cycle, there is a net loss of 1 positively charged ion out of the cell. This also makes the inside of the cell electronegative as compared to the outside. In a nutshell, resting membrane potential is generated by the diffusion of potassium ions out of the cell and electrogenic activity of sodium-potassium ATPase pump. This was short and sweet level 1. Now for advanced people, let's see the same concepts in more detail. First, regarding potassium. Its concentration inside the cell is about 140 milliequivalent per liter and outside concentration is about 4 milliequivalent per liter. This strong concentration gradient favors potassium exit. So potassium ions diffuse out through leak channels. Exit of positively charged ions generates inside negative electrical gradient. Now this electronegativity inside the cell attracts positively charged potassium back into the cell. With the diffusion of more potassium ions, this gradient gets stronger and stronger. Eventually, a point comes where electrical gradient is strong enough to prevent potassium diffusion down the concentration gradient. Thus, equilibrium is achieved where concentration gradient and electrical gradient are equal but in opposite direction. At this equilibrium, voltage tends to be minus 94 mV inside the cell. Now this is somewhat opposed by the diffusion of sodium. Sodium concentration is high outside and low inside. So sodium tends to diffuse from outside to inside. As they carry positive charge, their entry tends to move the voltage towards positive. However, during the resting condition, sodium channels are mostly closed. So the amount of sodium sneaking in is very small and the shift in the voltage is also very small. At this point, combined result of sodium and potassium diffusion is minus 86 mV inside negative potential. Finally, we have sodium-potassium ATPase pump. As we have already seen, it causes a net movement of positive ions out of the cell. This makes the cell electronegative. Its contribution is about minus 4 mV. So finally, we have minus 90 mV resting membrane potential in neurons. One more thing. Although the direct contribution of sodium-potassium ATPase pump is very small, it is very important. That is because potassium gradient, which is responsible for most of the resting membrane potential, is established by this pump in first place. That's all. In summary, again, resting membrane potential is established by diffusion of potassium out of the cell by potassium leak channels, with slight contribution coming from electrogenic activity of sodium-potassium ATPase pump. That's it for this video. If you feel this video will help your friends and colleagues, please share it with them too. And don't forget to subscribe because lots more to come. At Non-Stop Neuron, learning medical concepts is as easy as watching cartoons. Thanks for watching. See you in the next video.